Hello students, in this unit we are going to discuss nuclear energy and nuclear technology. Now, when it comes to nuclear energy or nuclear technology, every year if you look at the question papers, whether it is the prelims paper or the mains paper, we have had at least one question coming. Either it is asked in the prelims paper or it is asked in the mains paper. In 2017, we saw a question that came in the mains examination, a relatively easy question. Similarly, in 2016 also a current affairs based question on nuclear energy came, and that was also an easy question. You can call it easy given the fact if you know the basics that we are going to discuss here. So when we break up this entire unit, the very first thing that we have to start with is to understand what do we mean by a neutron and understand the concepts of nuclear force and nuclear energy. Then from where we'll move to the types of nuclear reactions that you have, but before that we'll discuss radioactivity, and then from radioactivity we'll begin our discussion on fission and fusion reactions, and then finally after this all discussion is done, then we'll move on to nuclear technology and we'll start that part with nuclear reactors. We'll see the basic components of a nuclear reactors, plus then after that we will look into the types of nuclear reactors, and then finally we will talk about the India's program for nuclear technology, that is India's 3-stage nuclear program. So this would be the last thing that we will discuss here, and then we will conclude the lecture. So these are going to be the most important parts for you to understand these areas. If you understand these areas, this is going to be very, very easy for you. So let's start. So the very first thing that you should know about the neutron, before we go into the nucleus, we'll see what exactly are the components of an atom. So what we know about the atom is that you have an atom which is very big, and at the center of the atom you have a very small part, very small compartment that contains two of the fundamental particles of an atom, that is a proton and a neutron. And apart from the atom, if we are talking about the entire atom, this is completely empty, only containing the electrons in different orbits. So this is how an atom looks like. Now when it comes to this part of atom, which is called as the nucleus of the atom, this nucleus is basically what is very tightly contained. Just think of the entire atom. I have 3 different components: electrons, protons and neutrons. Mass of a proton is 1.672 into 10 to the power of minus 27 kgs. For electron it's 9.1 into 10 to the power of minus 31 kg, and for a neutron it's 1.674 into 10 to the power of minus 27 kg. So if you look at mass of a proton and compare it with the mass of the neutron, what we see here is that these are comparable. Right? These are comparable quantities in terms of mass. If you talk about the electron, electron definitely is much lighter because it weighs a total of 10 to the power of minus 31 kg, which is much lesser than 10 to the power of minus 27 kg. So now, if we look at the mass of the entire atom, it is made of 3 constituents, right? Electrons, protons and neutrons. Now, protons and neutrons are completely contained under this compartment, that is the nucleus. So you can say in a way that most of the weight of the entire atom is contained in a very small compartment, which is called as the nucleus. Now, since I say that the mass is very high in this, so it is becoming very highly concentrated. So the amount of energy that should be there, which is binding this particular compartment, that is my nucleus, that is also very, very high. Since this is also very high, the nuclear energy that is contained in the nucleus, that is also a very high energy source. So if I try to break down, if I try to break this nucleus, the amount of energy that will be released, that will be very high. And that is the source for nuclear energy for us. Whether you talk about fusion reaction, whether you talk of fission reaction. And what is fission and what is fusion, we'll just come to it in the later part of this discussion. So the very first thing that we need to understand is how we came to the discovery of a neutron, because until the point that we had discovered neutron, we just knew one thing, that there are two charged particles that are there inside the atom, proton and electron. So now we knew that this has a positive charge and this has a negative charge. Now you have something called as an isotope. Right? You have something called as an isotope. What is an isotope? Isotope is when you have same atomic number but different mass number. For a given, this remains the same, this changes. So for a given atom, an isotope could be the different kinds or different variants that exists for an element. Why? Because when you talk of an atomic number is nothing but the number of protons that are there inside the nucleus, and when you talk of mass number is number of protons plus number of neutrons. So what happens is, for a given element, it can be present in various forms. For example, when we talk of hydrogen, hydrogen is present as hydrogen, deuterium and tritium. These are the three variants of hydrogen that is for the given element. So now what was seen is that the ratio of the nucleus of these three are in the ratio of 1:2:3. Now, if the masses are in the ratio of 1:2:3, what we know is that the number of proton is the same. All of them have one proton each. But still their mass numbers are different, or the masses are in the ratio of 1:2:3. So that means there should be something else that is there inside the nucleus. Now, complete charge of a nucleus is positive. What that means is, this kind of particle that exists apart from a proton is a particle which is neutral. So then this was discovered by a scientist, James Chadwick. So James Chadwick was the one who discovered the neutron when he did these experiments. So now what he saw that, okay, if there is the entire charge of the nucleus is positive, the mass is varying, it means that there should be some neutral particle also that has very similar mass as compared to proton, because the masses are in the ratio of 1:2:3. So then the discovery of neutron happened. With the discovery of neutron, the study of nucleus took a different turn. Until now, we were only discussing electrons and protons whenever the discussion of atoms started to happen. Now the discovery of neutron had happened. One more discovery, or one more very significant development that happened at this point, was the equivalence of mass energy that was done by none other than Albert Einstein. And this was the equation E=mc square. Now what was seen when we talk about this nucleus? Nucleus has two things that we know of, one being proton and one being neutron. Now, if let's say, if I am splitting this nucleus, then the mass of individual proton plus mass of individual neutron should give me the mass of this particular nucleus. But this was not the case. What was seen is that if you add up the mass of a proton and a neutron, this is something which is greater than the mass of that given nucleus. So the mass of nucleus was lesser than the combined mass of proton and neutron, and this is something which was named as mass defect. Similarly, for the energy also, the energy content of the nucleus was also seen to be lesser than the individual energy contents of protons and neutrons. So here also you had some differences. Until the point that this equivalence equation was given, mass and energy were considered to be two different things. So that all the study also that used to happen for mass and energy, they were also happening separately. Mass was considered for matter and energy was considered for as a source of energy. So there was no difference, or there was no similarity that was seen. But as soon as we had this equation, the scientists who were working on this particular field, they also started to look into this equivalence. So here came the theory of two new things, one being mass defect and then the second being binding energy. And what was seen is that binding energy, which were two things being governed by the same set of equation. Now from here on, the first thing what we need to know about, what is binding energy or what is nuclear binding energy. So what we know about the nucleus is that the nucleus is made of proton and a neutron. This is what we have done until now. So therefore, it may be expected that the mass of nucleus is equal to the individual mass of protons and neutrons, something that we just discussed. However, the nuclear mass is found to be always less than this, and the difference in mass of nucleus and its constituent is called as mass defect. So the theory of mass defect came from here. Apart from that, the mass of nucleus is said to be lesser than, as we have already discussed, the masses of its constituents. The equivalent energy of nucleus is less than that of the sum of equivalent energy of its constituent. So if I want to break a nucleus into its proton and neutron, an energy that is equivalent to delta mc square, delta m being mass defect or the difference in the masses, will have to be provided, and this is called as the binding energy of the nucleus. So the energy that is equivalent to the energy that will have to be provided to ensure that you are able to break this particular nucleus, this is the binding energy of the nucleus. So if we separate the nucleus into its constituent nucleons, nucleons basically is the word I use for either neutrons or protons. So for neutrons or protons, the common term that you can use is a nucleon. So for that we would have to supply a total energy that is equal to the binding energy of those particles. Now there is one more term that is used for binding energy, that is binding energy per nucleon. So what binding energy per nucleon means is the ratio of binding energy of the nucleus to the atomic number of the nucleon of that nucleus. So per nucleon, what is the binding energy, and this is what we are talking about. So if you look at this particular diagram, what you see is a graph of mass number against binding energy per nucleon in mega electron volts. So what has been observed is that the graph follows something like this. So what happens is the binding energy per nucleon is lower for the lower mass numbers and is lower for the higher mass numbers also. So for a very long time, let's say starting from 30 and going up to approximately 170, what we see is that the binding energy remains kind of constant. Binding energy per nucleon remains kind of constant, and this is approximately 8 mega electron volts. This is approximately 8 mega electron volts. So for the lighter nuclei and for the heavier nuclei, this binding energy is less. Now if binding energy is less, what means from here is that if a nucleus wants to attain a higher binding energy, suppose a nucleus wants to attain a higher binding energy, in that case what would it have to do? It would have to break. I am talking about a heavier nucleus. It would have to break. Suppose something here. Let's say you have something which has a mass number of 240. If it breaks into 120 plus 120 mass numbers, it comes in this area. And if it comes in this area, the binding energy that you have associated with that nucleus will also be higher. So if a higher nucleus wants to attain a very high binding energy, it needs to split. Now look at the lighter ones. If you look at the lighter elements, if they have to increase their binding energy, they need to fuse together. So if you have hydrogen, two hydrogen would have to combine together to form a helium nucleus which has a higher binding energy. So to attain a higher binding energy, the elements which are lighter and the elements which are heavier both would have to release some energy. That is when they would have a higher energy. So this release of energy that happens, this is something which is called as the binding energy. So now the binding energy per nucleon is, if you can see this, practically constant or independent of the atomic number for nuclei in the middle mass number range between 30 and 170. So the binding energy per nucleon is lower for both the lighter nuclei and for the heavy nuclei, that is less than 30 and more than 170. So the constancy of the binding energy in the range of 30 to 170 is a consequence of the fact that nuclear force is of short range. So this is a very, very important fact for us to remember. Now what we observed there in that graph is that a very heavy nucleus has lower binding energy per nucleon as compared to the nucleus with lower mass number. Thus, if the nucleus with higher mass number breaks into two nucleus with lower mass numbers, the nucleus gets more tightly bound. That is, the binding energy increases. And then the energy would be released in this process. And this energy release that would happen due to the split of this very heavy nucleus will be called as fission. Now, another case would be when we consider two light nuclei which have mass numbers less than 10, which would join together to form a heavier nuclei. So the binding energy per nucleon of the fused heavier nuclei is going to be more than the binding energy per nucleon of the lighter nuclei. This means that the final system is more tightly bound than the initial system. Again, energy would be released in such a process, and this is fusion. So in the first process, what is happening is that the heavier elements or heavier nuclei are splitting into lighter ones and thus releasing energy, and this is what you know as fission reaction. And in the second part, the lighter nuclei are fusing together to form a heavier nuclei, and this is when you call it a fusion reaction. So these are the two types of nuclear reactions that you have. Now, the force that you have between or inside that nucleus is something that is called as nuclear force. Now, if you look at this, the average mass nuclei, for an average mass nuclei, the binding energy per nucleon is approximately 8 mega electron volt. This is something that we have seen, which is much larger than the binding energy in atoms. When you look at atoms, it is in terms of electron volts. When you talk of nuclei, it is seen in terms of mega electron volts. So that's why there is a huge difference between the energy content of the atoms and as compared to the nuclei. So to bind a nucleus together, there should be one kind of force that is much stronger than the Coulomb force or the atomic force. That's why it would be able to overcome the force, right? Because there is a force that would exist between two protons, or a proton and a neutron, or two neutrons. So the force of repulsion, let's say there would be a force of repulsion which will be there between two protons. And this force of repulsion has to be overcome, because inside the nucleus, you are ensuring that all the protons and all the neutrons are concentrated in that very heavily concentrated space. So there would be very strong repulsion between all the protons that would be present inside the nucleus. So you have to overcome this strong force. So that's why for this particular force, that is the nuclear force, this needs to be even stronger. So this is something which you know as a nuclear force. The stronger force that exists inside the nucleus, that is able to bind the entire nucleus and the contents of the nucleus together, is called as the nuclear force. So that's why the nuclear force that exists between two neutrons, a proton and a neutron, and two protons is approximately the same. It is independent of the electric charge. It does not depend on electric charge. This is a very important statement from prelims point of view. So just remember that this force that we are talking of, that is the nuclear force, is independent of the charge. So that's why whatever charge be present on the protons, or if there were another charge source, this force will be completely independent on that.